Last year, attackers found a way to hide in plain sight. They didn't use noisy malware. They didn't trigger obvious firewall alerts. They used something every computer already trusts: DNS, the same service your computer uses every day to find websites. But this time, those DNS requests carried something else. Those were commands, tiny pieces of stolen data moving out of the network one request at a time. That's what makes attacks like this so dangerous. They don't always look malicious, they often look completely normal. And that's the uncomfortable truth. The technologies we are about to learn in this video: IP addresses, ARP, and DNS. They weren't designed with modern cyber attacks in mind. Attackers simply learned how to abuse them. So, this week, you are not just learning how computers communicate, you are learning how attackers communicate too. I am Netra. Welcome to second week of networking. To understand how computers communicate, you only need 4 building blocks. First, IP addressing. Every device on a network needs an identity. Without it, nothing knows where to send data. And the second is subnetting, the secret that divides one big network into smaller, organized neighborhoods. Don't worry, we'll make it simple. Third, MAC addresses and ARP, the technology that helps devices find each other on a local network, and the weekends attackers exploit with ARP spoofing. And finally, DNS, the internet's phone book. It turns names into IP addresses, and it's also one of the most abusive services in modern cyber attacks. Every device connected to a network needs an address. Without an address, data has no idea where to go. That address is called an IP address. IP stands for Internet Protocol. It is the set of rules that governs how data is formatted, sent, and received over the internet or local networks. The version you will see most often is IPv4. IPv4 is made of 4 numbers called octets. Each number ranges from 0 to 255. For example, 192.168.1.10. Behind the scenes, that's a 32-bit address that gives us about 4.3 billion unique addresses years ago. That sounds like more than enough. But today, billions of phones, laptops, servers, smart TVs, and IoT devices all need addresses. Eventually, IPv4 ran out. Now, IP addresses live in two different worlds: public and private. Public IP addresses are globally unique. They are visible on the internet and can be reached from anywhere. Private IP addresses are used only inside local networks like your home or office. They are reused all over the world. You will see these 3 private address ranges anywhere: 10.0.0.0, 172.16.0.0 through 172.31.255.255 and 192.168.0.0. If you have ever connected to your home Wi-Fi, there is a good chance of your device had an address starting with 192.168. That address exists only inside your local network. It doesn't exist on the public internet. So, how does your laptop reach website on the internet if it only has a private addresses? That's where NAT comes in. Network Address Translation. When your device sends traffic to the internet, your router replaces your private IP address with its own public IP address. It keeps track of which device started each conversation, so when the reply comes back, it knows exactly where to send it. That's why dozens of devices in your home can all share one public IP address. Without NAT, 2 more terms you will hear often: a static IP address never changes. That's commonly used for servers because clients always know where to find them. A dynamic IP address changes over time. It's automatically assigned by the DHCP server. That's what your laptop or phone usually receives every time it joins a network. Remember DHCP? We'll come back to it when we learn ARP. Now, here is the part many tutorials skip, and it's important today. NAT bought us time, but internet providers eventually ran short of public IPv4 addresses too. So many providers introduced something called carrier grade NAT or CGNAT. Instead of one home sharing one public IP, now hundreds of homes can share the same public IP addresses, which means the public IP you think belongs to you often doesn't. For a SOC analyst, that's important. One suspicious public IP address might actually belong to hundreds of different customers. Tracing an attacker back to one specific person becomes much harder. So, what's the long-term solution? IPv6. Instead of 32 bits, IPv6 uses 128 bits. It's written as 8 groups of hexadecimal numbers. The address space is enormous, so large that address shortages are no longer a practical concern. IPv6 was designed so NAT is generally unnecessary. So many organizations still use translation technologies during migration, but IPv6 gives every device enough address space to communicate directly. IPv6 adoption is growing rapidly around the world. India is one of the world's leading adopters of IPv6. Many internet providers already deliver IPv6 to most customers. Cloud platforms increasingly support IPv6 by default. If you are preparing for a SOC career, IPv6 is no longer optional. Now, here is the part that directly affects security. IPv6 is not automatically safer than IPv4. Three things every SOC analyst should remember. First, the IPv6 address space is so massive that attackers can't simply scan every addresses like they often do with IPv4. Instead, they use smarter, targeted techniques to discover systems. Second, most organizations don't run only IPv4 or only IPv6. They run both together. This is called dual stack. Now, your network has two communication paths instead of one. If your security tools only monitor IPv4, IPv6 traffic may pass through your network without being inspected, and you can't defend what you can't see. Third, IPv6 has its own version of attack we'll learn later. The next is subnetting. Subnetting sounds scary, but it's actually very simple. Imagine a large office building. Instead of putting every employee into one giant room, you divide the building into separate departments: finance, HR, sales, and IT. Each department has its own space. A network works the same way. Instead of one huge network, we split into smaller networks. These smaller networks are called subnets. Why do we do this? First, it keeps the network organized. Second, it improves performance because devices don't all compete on one large network. But for a SOC analyst, there is even a bigger reason: security. Imagine an attacker infects one employee's computer. If every device belongs to one giant network, the attacker can move almost everywhere. But if every department is placed inside its own subnet, the attacker gets trapped. Finance stays separate from HR, and HR stays separate from IT. The subnet becomes a security boundary. Now let's talk about the subnet mask. You'll usually see something like /24. That number simply tells us how much of the IP address belongs to the network and how much is available for devices. You don't need to memorize the math today. Just remember one idea. A smaller slash means the larger network. A larger slash means a smaller, more controlled network. We'll practice the calculation in later session. Now, here is why subnetting matters even more today. Almost every cloud platform, AWS, Azure, Google Cloud, uses subnets everywhere. Public subnets, private subnets, database subnets, application subnets. It's the same concept, just inside the cloud. Modern security also follows something called zero trust and control who can communicate with whom. Finally, here is why subnetting matters inside a SOC. Imagine you receive an alert. A server inside the database subnet suddenly starts communicating directly with the internet. That shouldn't happen. Even before opening the logs, the subnet already tells you something is wrong. So far, we have learned that IP addresses help data travel between networks. But once that data reaches your local network, something else takes over: the MAC address. Think of an IP address as your home address. A MAC address is like the person's identity inside that home. Every network device, your laptop, phone, router, comes its own unique MAC address, unlike an IP address. A MAC address usually stays with the device. Now, here is the question. Imagine your computer wants to send data to another device on the same network. It already knows the destination IP address, but it doesn't know destination MAC address. So, how does it find it? That's where ARP comes in. Address Resolution Protocol. Your computer simply asks, who has this IP address? Every device on the local network hears the question. Only the correct device replies, that's me. It sends back its MAC address. Your computer remembers that answer, so it doesn't have to ask again every time. Simple. Now, here is the problem. ARP was designed decades ago, when nobody expected attackers inside the network, so ARP trusts every reply it receives. It never checks whether the reply is genuine. That's the weakness. Now, imagine an attacker joins the same Wi-Fi network. Instead of saying quiet, the attacker lies. It tells your computer, I am the router. At the same time, it tells the router, I am your computer. Both devices believe the attacker from the moment. Every packet passes through the attacker's device first. This is called a man-in-middle attack. The attacker can watch traffic, capture passwords sent without encryption, redirect users to fake websites, or steal session cookies. While everything appears normal to the victim, so how do enterprises network stops this? Modern switches doesn't trust every ARP reply anymore. They build a trusted table of which IP address belongs to which MAC address. When the fake ARP reply arrives, the switch compares it with the trusted table. If it doesn't match, the packet is dropped immediately. The attacker never reaches the victim. For a SOC analyst, these dropped ARP packets are valuable alerts. If you suddenly see many ARP validation failures or one device pretending to own multiple IP addresses, someone may be attempting a man-in-middle attack inside the network. Think about your computer. When you search for google.com, your computer doesn't understand that name. It needs an IP address. That's where DNS comes in. DNS stands for Domain Name System. Think of it as the internet's phone book. It simply translates a website name into the IP address your computer needs. Here is what happens behind the scenes. When you type a website name, your computer asks a DNS server, what's the IP address for this website? If the DNS server already knows the answer, it replies immediately. If it doesn't, it asks other DNS servers on the internet until it finds the correct answer. Once it gets the answer, it remembers it for a while. That's called DNS caching. That's why websites usually load much faster the second time you visit them. Now, you will hear about different DNS record types. Don't try to memorize all of them today, just remember these 5. A record returns an IPv4 address. 4As record returns an IPv6 addresses. CNAME points one name to another. MX record tells email where to go. TXT record stores extra text information. But attackers found a way to abuse them. Here is how. Every computer on the internet is allowed to send DNS requests. If DNS stops, the internet basically stops. So firewalls almost always allow DNS traffic. Attackers takes advantage of the trust. Instead of stealing data through suspicious connections, they hide the stolen data inside DNS requests. One small piece at a time. The DNS request looks perfectly normal. It passes through the firewall, reaches the attacker's DNS server, and the hidden data is extracted. This attack is called DNS tunneling. It's one of the ways to steal data out of a company. Real world attackers have used this technique in major cyber attacks. That's why SOC analysts pay very close attention to DNS activity. But there is another challenge today. Modern browsers support encrypted DNS. Technologies like DNS over HTTPS and DNS over TLS hide DNS requests inside encrypted traffic. This protects user privacy, but it also makes network monitoring much harder. Instead of reading the DNS request directly, analysts now look for unusual behavior, very long domain names, thousands of DNS requests to one domain, or strange DNS record types appearing repeatedly. Those patterns often tell us something isn't right. That's why DNS logs remain one of the most valuable sources of evidence inside a security operations center. If you can understand DNS, you will investigate incidents much faster and become a strong SOC analyst. Let's lock in what you have learned today. You now understand how every device is identified using IP addresses, why private IP needs NAT, and why IPv6 is becoming the future of networking. You have learned how subnetting divides network, improves security, and helps contain attacks. You discovered how devices find each other's using MAC addresses and ARP, and how attackers abuses the trust with ARP spoofing. Then you explored DNS, the internet's phone book, and saw how attackers hide stolen data using DNS tunneling. You also learned why encrypted DNS makes detections more challenging and why DNS remains one of the most important log source for every SOC analyst. Next week, we move from theory and real packet analysis. You will learn the OSI model and see exactly how packets move across the network. Subscribe to TrinetraSOC right now. Hit the notification bell so you never miss a single video. The digital world needs defenders. I am Agent Netra and I will see you in the next video.